Yeah.
Do you want to see if you can share your screen?
Yeah. You see this?
I think it's about to appear. Yeah.
Nice.
Great.
Cool. When do I start?
In any minute, if you are ready.
Okay.
Yeah.
Cool. Yeah. Thanks for the organizers for organizing this nice little workshop. Yeah. Let me just dive straight into it. So let me paint the scene for you first. So suppose you're exploring some new technique. You start small. You work on a toy problem first, and you got a nice training curve that looks like this, for example. I mean, in particular here, I'm actually plotting like a very small training curve, but whatever situation, you have some nice training curve, and then you want to test it on a larger scale problem, a larger model or larger data set. And oftentimes, you actually can be unfortunate, and when you scale up, your model actually fails to train and diverges very quickly. So this is, this can be quite common. Depends on the setting you're in. And this means, possibly two things. One, it could be that the new technique you're proposing just doesn't work on larger scale, or it could be that you just need new hyperparameters for the large scale problem. And you don't really know until you do hyperparameter tuning. Now, if your target problem is not that big, then yeah, just do hyperparameter tuning, and you probably will end up fine. But as you scale up more and more, and up to like modern neural network sizes of like large pre-trained vision or language models, which have billions up to trillion of parameters, you just cannot afford to tune hyperparameters because it's way too expensive to even run a single model. So this problem, which it really is not a problem, not a huge problem for small sizes, becomes absolutely critical for large size problems. And what this work allows you to do is train reliably any large models by scaling up your small model, right? So you would get a curve that looks like the orange curve on the right side rather than the orange curve on the left side. And this is the result of our work on tuning large neural networks via zero-shot hyperparameter transfer. And this is the fifth installment of Tensor Programs series, and the first large, large payoff combination of all the theoretical work that we did in the past in terms of an empirical result. And this is in collaboration with Edward Hood and others from Microsoft and OpenAI. Okay, so before I keep going forward and give you the details, let me kind of lay out the larger picture here. So, here I have a picture of the Manhattan Project and the space program. So what do they have in common? Well, they're definitely revolutionary achievements of their times that started technological races between nation states. But actually, I want to really point out the scientific aspects of these projects. So in each project, the empirical test is very expensive, right? Like, like testing a single atomic bomb, building and testing a single atomic bomb versus, also like launching a space shuttle. These are all very expensive. And, before any test, you require extensive planning in order to pull these off. And in each of these, like physics contributions to physics and other theorists are absolutely critical in order to ensure the safety and the feasibility of each project, each empirical run. And in my view, like today, the trend today of large pre-trained language and vision models are following the same bucket as these things. So in recent years, they definitely have revolutionized and shifted our perception of what machine learning is capable of in terms of approaching human level intelligence. It also started races definitely between top corporations and nation states. But again, I want to really focus on the scientific aspect of this, which is that training each large language or vision model is extremely expensive. And I mean, today, the city-R model is probably upwards of $10 million per each training run. But this is gonna go up for sure, as time goes by, as these models become better and better. And as such, they really require a lot of planning to pull off. Now, probably one difference between this large pre-trained language and vision model and the Manhattan Project and space program is that so far theorists are not so involved in this planning stage. And I think that's an arbitrage opportunity because just like these two projects, like these things can be very fragile when you try to train really large models. And having a good theoretical grasp of what large models do will give you a very good tool to answer the question of how to train these models reliably and optimally. And like the picture I showed you earlier of training BERT small to BERT base, even that problem, if you're being naive, you can run into divergence very quickly. So in this work, we propose a very simple solution for at least some aspect of this question. And the solution is just to reparameterize your model in something called the maximal update parameterization, which was introduced in Tensor Programs 4, and which I gave a talk on a year ago at this exact conference. But the gist is that in the standard parameterization, well, it turns out as you scale up your model, your optimal hyperparameter will shift. So if you naively just tune your hyperparameter on a small model and just fix it as you scale up, you will do not so well on a large model. However, if you just switch to this parameterization, then magically your hyperparameters are stable. Optimal hyperparameters are stable across width, and in fact, you also just do better overall as compared to if you use standard parameterization. So here, the transfer means like transferring hyperparameters means that the optimal hyperparameter remains stable with model size. So like the optimality here is the key concept here. And we call this the mu transfer technique. So obviously we had to really validate this result on a variety of benchmarks and tasks in order to make this claim. But we did that, and ultimately we're very confident that it's robust and reliable. So on a variety of things like language modeling, machine translation, BERT GPT, ResNet, ImageNet, all kinds of stuff. So I'm not going to explain all these plots right now, but I'll get to them later. But the point is that up to from a small scale to a large scale on different tasks, this is a very reliable way to scale your hyperparameters. Okay, so now let me talk about kind of theoretical intuition behind why this works. So if we want to scale models reliably, we better understand how large models behave. And let's just think about like how wide neural networks behave currently. So what happens when you take the width of a neural network to be very, very large? Well, if you're in a standard parameterization, just like the default in PyTorch, for example, then you're gonna actually just blow up very quickly when your model is very wide. And you can say, okay, let's just lower the learning rate then, no biggie. But it turns out if you want to lower the learning rate so that it doesn't suffer from gradient explosion or model training divergences, then you will get no feature learning in the infinite width limit. And that is really, really bad for the purpose of pre-training because pre-training is all about absorbing the features from the data set, like the Wikipedia or Reddit or like all kinds of data set on the internet. And not being able to absorb those features means that you trained your model for nothing and you wasted $10 million. Congratulations. Now, on the other hand, the maximal update parameterization has the critical capability of maintaining feature learning as you go to the infinite width limit, and also it doesn't blow up. So if you're given a choice between standard parameterization and maximal update parameterization, obviously you should choose the latter. However, it's not just like that. The mu-p is an abbreviation for maximal update parameterization. It's not just mu-p is better than standard parameterization, but rather, in fact, it's like the optimal parameterization among like the moduli space of parameterizations in some sense. And in the sense that it's the unique parameterization that maximally emits feature learning in the infinite width limit. And this is a key property that singles it out and allows hyperparameter transfer. And the brief intuition here is that as width becomes large, your model converges to some infinite width limit, and so the hyperparameter landscape at that limit is some landscape, and you expect that as the width becomes large, your hyperparameter landscape for a finite neural network should also converge to that landscape, and as such, the optimal hyperparameter, right, or the peak of that landscape should be stable with width as soon as your width is large enough, which is kind of like the picture on the right. Okay, so now let me give you some intuition on how to derive such a parameterization from first principles. Now, I just note that I haven't actually told you in concrete words what exactly the parameterization is, but let me try to derive it from first principle in an intuitive way. So what you might want to do is first write down a list of desiderata for what constitutes a good parameterization. And this can evolve the following. So anytime during training or initialization, every activation or pre-activation vector should have a constant size coordinates, where constant size means constant in width. Second, the network output should be similarly constant bounded. Third, all parameters should be updated as much as possible without leading to divergence. And this is the third one is the crucial point behind why maximal update parameterization is maximal update and why it maximally emits feature learning. So hopefully this looks fairly intuitive. And once you accept these desiderata, then deriving mu p is somewhat similar in spirit to deriving the renormalizability of an effective field theory, i.e. you end up doing some dimension analysis in width, right? Just like you do dimension analysis in the cutoff in effective field theory. And then doing dimension analysis will lead you to calculate, like this thing should scale this way, this thing should scale this way, so that like all these three conditions are satisfied. Now, of course, like doing the actual math will involve more than just just saying to do dimension analysis. It's a bit more complicated than that, but the spirit is similar. Okay, so finally, here's what the parameterization actually looks like. So in particular, this table tells you how to scale different hyperparameters like initialization variance or learning rate with HED or Atom for different parameter tensors in the network. So input weights, biases, output weights, hidden weights. And here I want you to focus on the scaling with fan in and fan out. And ignore the constants like the 1 or the eta, like those things that they are tunable constants. Those things don't matter so much here. The thing that matters is the power that goes with the fan in or fan out. And here I'm highlighting the difference between the maximal update parameterization and the standard parameterization in purple. So these are the main differences between these parameterizations. In particular, in practice, what really matters is the Atom learning rate, because for these settings, everybody uses Atom, like HED doesn't work. So I'm not sure how familiar people are with Atom, but this is quite unusual from a common perspective, from a practitioner today's perspective. And so you can see how it will be somewhat difficult to stumble upon this kind of parameterization if you are not being very serious about the theory. Okay, let me maybe pause a little bit here. Anybody has a quick question?
Sorry, can you say again what fan out and fan in are in terms of the width?
Yeah. So you have just consider like a matrix, like a weight matrix. Fan in is like when you multiply. Okay, fan in is like the right side of the matrix. Fan out is like the left side of the matrix, essentially. Like the output dimension of the matrix. And fan in is the input dimension of the matrix.
Oh, okay, that's what I was guessing, but thanks.
Yeah. All right, so let me keep going. And this section, just to convince you that this is like the simple reparameterization really gets the job done. And we can start small with a 200 layer MLP on CFAR10. And if you're in standard parameterization and you try to scale up your model by making it wider and wider, and you plot the training loss versus learning rate after training, then you'll see that first, the optimal learning rate shifts quite a bit as you get really large. And two, you actually do worse as you get wider. And if you just reparameterize, you see this very nice curve that the optimal learning rates all coincide, and going wider always gives you better performance. Okay, so we can do something more complicated. Let's do transformer Wikitext 2, which is a smaller language modeling data set. And again, if you're in standard parameterization, your optimal will shift by quite a bit. But if you just reparameterize in maximal big parameterization, then you see that the learning rate essentially, like the optimal learning rate, also the other hyperparameters like the cross entropy, temperature, the initialization standard deviation, the learning rate schedule even, they remain stable with width. Okay, we can go to a larger size problem. So let's try tuning BERT. And here, what we did is we'll first parameterize BERT in UP. Second, we can tune a small version of BERT via random search here. But like in practice, you can use whatever technique you want to do the hyperparameter tuning. But here for science, to be consistent, we use random search. And finally, we just copy the best hyperparameter combination into BERT base and BERT large. So like it's really quite simple conceptually. And here's just to give you some notion of like the size of models we're talking about. So BERT small is 13 million parameters, but BERT base and BERT large is like 10 to 30 times larger. And you have a corresponding 4 times or 22 times speed up of the training costs of each model. So once we perform this experiment, we get the following training curves. And here, the orange curves are the baseline, and then the dashed curve is for BERT base, and the solid curves are for BERT large. And the blue curves are our retuned version. And as you can see, like essentially throughout training, just the retuned version of BERT just works quite a bit better. And similarly, you can tune the models downstream on glue tasks, and you get the same thing. Like on downstream tasks, you also see a performance boost. Okay, we can even go larger. We can try GPT-3. You can first verify, okay, again, learning rate stable with width, everything we did previously. Also, wider is always better given the same hyperparameters. And we went to ridiculous sizes like 32,000 for the width. So this is like a couple billion parameter model. And we see a very beautiful trend of the curves still continue to get better and better as you increase width, which cannot be said really for naive scaling. And finally, we seriously retuned the 6.7 billion parameter model of GPT-3 using new transfer. And this is the learning curve you get. But the point is that essentially by just using 7% of the training budget for GPT-3 6.7 billion, we completely kind of blasted that baseline model. And in fact, we achieve a performance comparable to the 13 billion parameter model. So in other words, like by just retuning the 6.7 billion model from the GPT-3 paper, we effectively doubled the size of the model. I mean, almost for free. Like the cost was just 7% of the training budget. Okay, so that's all I'm going to say about the empirical results. Let me pause here briefly to just answer any questions.
Can I quickly ask one?
Sure.
Hi, Greg.
Yo, what's up, dude?
I just want to quickly ask, do you have a theoretical control on the lower limit? So where you start from scaling up? Of course, if you made your model too small, then, I mean,
yeah, if you make your model too small, yeah, like if you have one neuron, it definitely is not going to work.
Exactly. So do you have theoretical, do you have theoretical control on sort of when this scaling law works?
Yeah, that's a very, very good question. Essentially, the answer is no. And like for the like empirically, if you want to use this technique, we found just like 256 or something, like with 256, 128, like those ranges work pretty well across the board. So empirically, that's what we would recommend. Now, like I think it's an interesting question. Like, how can you theoretically control, you know, like the lower ranges, you know, of the small model, but I also like note that it's not necessary like, you know, if you have the small model size, you get like twice the gain, because GPUs, they're kind of not optimized for small models. So even if you have the width, you might get like 1.5 times gain or even 1.2 times gain as you go smaller and smaller, just because GPUs are not optimized for those things. So I think 256 is like a pretty sweet point between like empirically, like the transfer works well, and also GPU is relatively optimized for that size.
Great, thank you very much.
Okay, so let me continue.
Okay.
Okay, sure. Is it quick or?
I think so. So you mentioned some case where SGD doesn't work, and you're tuning hyperparameters. So my question is, you know, there's a kind of measure or prior on that space, and I've noticed some cases, many cases actually, where if you try to optimize, say, the friction versus with momentum, say, so there's a friction parameter versus optimizing the log of that, you know, some papers have claimed that SGD didn't work, but that was based on hyper optimizing the friction as well, as opposed to its log. And if you do the log with the same hyper optimization package, it finds a better solution for SGD. So I'm basically asking, yeah, how do you deal with that?
Yeah,
question?
we're agnostic to that, because that's like how you tune the small model. Like we're just saying, okay, after you tune the small model, here's how you pop the hyperparameters back to the large model.
Yeah, I got it. It's exciting that you can scale it up. I understand.
Yeah, great. Thanks for the questions. I think this is the interesting part probably for this audience. So I find that there's a really interesting analogy between large model training and effective field theory, especially in this context of hyperparameter transfer. Now, I need to make a disclaimer. I'm like a poser in terms of physics. I don't really know any physics. I just like know how to speak in that language, I suppose. So I'm gonna try to make that analogy based on what I know, but feel free to shout out anything you feel like I didn't say correctly.
You have about 5 minutes.
Yeah, sure. So the momentum energy cutoff in effective field theory is kind of like the model size in large model training or any other compute hyperparameters like training time. And coupling constants in effective field theory is like non-compute hyperparameters like learning rate. And a theory skeleton, which I mean the like a theory without specifying the coupling constants, corresponds to parameterization, by which I mean like kind of the way you scale different hyperparameters with like fan in or fan out or other compute hyperparameters. And a concrete effective field theory is a function of the momentum energy cutoff and the instantiation of the bare coupling constants, whereas a trained model is a function of the compute hyperparameters like model size, training time, batch size, and non-compute hyperparameters like learning rate, weight decay, and so on and so forth. Now, you know, we can get to a more meta level, like, you know, a physical theory should predict a fundamental physics of our universe, whereas like the model should predict, you know, when next word, a sentence, image, label, and so on and so forth, like human behavior. And in physics, the objective is to find coupling constants that reproduce experimental results as closely as possible. Whereas in large model training, the objective is, or like in our context of hyperparameter transfer, is to find best hyperparameter for a given size to train model to reproduce human language and vision as closely as possible. And the correct, whereas, you know, you can try to ask for the correct coupling constants in physics because you believe that the correct theory should reproduce the experimental results exactly. But in machine learning, at least currently in the near future, we don't expect any neural network to replicate human behavior exactly. So we can only ask for optimal hyperparameters for that given size of the model. Now we can, you know, take this analogy a little bit further if we specifically consider width as the measure of model size. But I mean, the general idea should also apply to other compute hyperparameters. Now, then the cutoff in effective field theory corresponds to model width, and the ultraviolet limit corresponds to infinite width limit of models. And this is kind of the interesting part, I think. You know, in field theory, you have the RG flow where you take the coupling at some cutoff and you run it to some other cutoff, and you get another coupling that should correspond to measuring, you know, the coupling at that energy level. And in hyperparameter transfer, essentially the same idea, like you tune your hyperparameters at a smaller width, and you have a function f essentially, which comes from the parameterization that gives you the right set of hyperparameters, HP prime at a larger width prime, right? So like these kind of like these ideas are rather almost identical. So then a renormalizable theory in the sense of like the physical coupling constants have ultraviolet limits correspond to parameterizations that emit hyperparameter transfer. So that the optimal hyperparameters have infinite width limits. And so we expect them to remain stable when the model width is large enough. The goal in, you know, field theory, I guess, or physics in general, is to come up with a theory that describes nature. And definitely some set of people in physics want to come up with a theory that describes nature at any energy cutoff. I guess some people, other people probably don't care. Whereas for large model training, the goal is to train large models reliably and optimally using parameterizations emitting hyperparameter transfer. And as an example, you know, in physics, you have QCD, and the ultraviolet limit is an asymptotic free theory, which describe, you know, quite a range of phenomenon for strong interactions. And you know, on the other side, the positive example for hyperparameter transfer is the mu parameterization, and its infinite width limit, the feature learning limit, aka the mu limit. As I've shown, this really predicts the optimal hyperparameters as you scale up the model. As a negative example, classical electromagnetism, I guess the ultraviolet limit is itself, but I mean, obviously it's not the right theory when you get to high energy levels because of things like ultraviolet catastrophe. And likewise, you know, you can, in neural networks, you also have other parameterization, you know, like the standard parameterization I've shown you, but also things like neurotangent parameterization. And their infinite width limits are both kind of kernel style limits. And they just are incorrect just because they don't transfer the optimal hyperparameters. Or rather I say like they don't describe neural networks in the regime we're interested in. So here's some open problems after all this discussion. So MIP solved the transfer problem for width in a principal way. You know, we also tested the MIP for depth and other hyperparameters, and they kind of work empirically okay. But as we go to larger scales, likely they will break down. So the question is, can we come up with the same theory and same confidence for scaling hyperparameter as other compute hyperparameters? And the analogy in physics is kind of like, you know, we have renormalizable QCD, but we're looking for a renormalizable theory unifying all fundamental forces of nature. And I think a good question to ask yourself is that you have $10 million to throw at a model training. Like, you know, for any theoretical candidate, are you confident enough about the theory to like scale your hyperparameter that way? Like if you want to throw down $10 million of your own money, like will you be willing to do that? I think that's a limits test. And secondly, after all this discussion, I think there is a very intriguing question of, can techniques from physics like effective field theory or even QFT and other related areas help with coming up with these understanding of other compute hyperparameters? Okay, so this is the last slide, and I just want to reiterate how important this problem of hyperparameter transfer is. This is a very high impact problem because it directly, you know, affects how large model training works. And large model training is a modern space race. Like we literally have larger corporations and nation states fighting. I mean, like friendly fights really currently, but hopefully not devolving into non-friendly fights. But definitely very heated race between companies and nation states. And these large neural networks are definitely the closest we have to human intelligence. And depending on how things go, they can significantly reshape everybody's lives in the upcoming years. So very, very high impact. But for theorists, it also has high leverage. And it's just because what I said earlier, each model training run can cost tens or more millions of dollars. And theorists here are absolutely crucial to provide guidance because empirical approaches are just way too expensive, right? And it probably can cost more. I can definitely see the US government throwing like $1 billion on this because it threw probably $10 billion on the space program. But we don't really know how to train models at large because there's too many things unknown. So I think with the right theory, the right theoretical insights, we can even understand how to spend $10 billion on this. And finally, I think also this is a very good test of proposed theories in deep learning. So, theoretical deep learning is very active just because deep learning is very active. But with that, there's comes a lot of I guess spurious theories in some sense. Not necessarily made in bad faith, but there's a lot of spurious theories with no predictive power. And the high stakes of this kind of setting means that all these fluffs theories will be weeded out very quickly, kind of like testing physical predictions using data from LSC. In particular, like what our work shows is that the correct limits of neural networks should necessarily omit hyperparameter transfer. So like as a corollary, anything based on NTK should not be correct in that sense because they do not omit hyperparameter transfer. Of course, like this is not, unexpected. I think people have at least in core theoretical deep learning have kind of tried to move on where have known that NTK is not the right limit for some time, but this is kind of like a definitive, I guess like if in a practical sense is a very definitive answer. So that's all I have. Thanks for listening. Here's the QR code for the paper if you want to check it out. Happy to take questions, I guess, but I guess over time.
Fantastic. Thank you very much for another really interesting talk. It's been a great session of talks today. We certainly have some time for questions, and this will sort of go on. We've got a 1 hour time for discussions that follows straight on now. So I think, Jim, you had your hand up first.
Hi, Greg. Great talk. I liked your use of the word moduli space at the beginning. So my understanding of what you mean is that you have these different weight initializations and how they scale with n, something like that. And you call these ABC parameterizations in your paper. And so NTK in that case is 1 point in the moduli space of initializations or something like that. It seems natural from a physics perspective to study the evolution of correlation functions during training as a function of that moduli space. Have you looked into that or thought about it? I mean, my understanding of sort of why this works from your paper from, I guess, a year ago or something is basically that if you make bad choices, things get shut off with respect to learning, or they explode, and you want to carefully tune so as to maximize feature learning. Have you studied sort of correlation functions as a function of mu p and slight perturbations around it?
No. Okay, so actually, it's maybe a bit nuanced. So definitely, like for 2-point function, that's very natural in machine learning because they correspond to kernels. They're kind of measure of how good your features are. So, kind of like I give them. I've talked about this in previous talks before, but like, one common way of testing how good your features are is just like train a linear layer on top of your last layers, and that essentially corresponds to like taking the kernel and doing kernel regression, and the kernel is a 2-point function. So in that sense, yeah, we care a lot about the 2-point function, but it's not so natural to care about like 4-point functions or anything beyond 2 in machine learning. So yeah, not in that sense, not in the sense if you care about more than 2-point functions. But for 2-point functions, we have experiments, for example, like tracking the evolution of how good the kernel is on a CPAR10 or something over the course of training.
And what about 1-point functions, which are kind of the central object in supervised learning?
Sure. I mean, I guess like, what do you want to say about them? Yeah, like they're of course very central, so we play with them a lot.
Yeah, exactly. I guess how the different choices of mu p affect the evolution and performance of the 1-point function in making predictions.
Oh yeah, on task where feature learning is important, of course mu p does way better than like I don't know, NTK parameterization or whatever standard parameterization.
And you guys understand that theoretically?
I mean, it depends on what you mean by theoretically. There's a lot of things to say theoretically. So I guess like for me, like the benchmark is like, can you affect a increasing performance in downstream tasks? Like that for me is passing the bar. And you know, like of course you can say a lot of theoretical things that don't necessarily lead to that conclusion. But I tend not to focus on those things that don't have an like realized benefit.
Thanks. I'll hold the rest of my questions.
Yeah, sure. What's up, David?
David.
Hi, yeah. I was wanting to ask about this analogy with the renormalization group. And there was a bit where you spoke about, I mean, I guess I'm asking, where's the infrared and where's the ultraviolet?
Yeah.
So there was a bit where you said ultraviolet, you know, asymptotic freedom. Intuitively, it would seem more like as you go to the large width limit, you're more likely going to the infrared in some sense. But I don't know.
Yeah, so maybe like one way to think about it is like ultraviolet is where you need a lot of money to do experiments, and training large model is where you need a lot of money to train large models, and you definitely don't need a lot of money to train small models. I mean, there's really isn't an infrared limit in neural networks. Is you like in physics, like you can have arbitrary like large wavelength, but like in neural networks, you have one neuron. I mean, that's the smallest neuron you can have.
Yeah, I mean, one of the ways that one might think about it is that as you, I mean, I would think of it's more like the amount of data that you've got is more like the amount of training data is more like the limits that you take, and as you add more data, then you are sort of going to the infrared in the theory because you're, or rather going to the ultraviolet, yeah, because you are integrating out less, something like that. Whereas stuff that you don't know, when you've got small amount of data, which is some sample of some whole infinite set of things, then you're having to integrate out loads of things to get an effective description. Whereas as you add data, you're adding in real things and integrating out less. But
okay, so I understand your perspective, but another way to look at it, which is the opposite, which you're suggesting, is that like like when you have very little data, you can only learn like lower Fourier modes of the data in some sense, and it's only like the fine features which are correspond to like higher Fourier modes can only be learned when you have enough data. So in this sense, like as you get more and more data, you're really going to ultraviolet because you're learning the higher modes.
Yeah, okay, I agree with that. Yeah. So as you get more data, you're going to the ultraviolet. Yeah, I agree with that. Yeah. Okay, thanks. Thank you.
Yeah.
Very good. So we have time now for